Let's talk about solving inequalities and how that kind of evolves over the years. We're going to focus explicitly on sixth grade moving up, our secondary levels. We'll come back to this chart at the end, but it's just a real quick, simple flow chart of how inequalities show up, how they're tested, and how we work with them throughout the years. This extends beyond Algebra 2 and on into pre-cal and even college algebra. They don't go away. They just get more complex. All of the inequality solving we do is based on the same rules as the equations that layer year by year. So in sixth grade, for example, every equation is a single variable. It is only one step to solve, and the coefficients are all whole numbers. And then it builds from there. Inequalities, however, start in first grade. In first grade, they look within 100 and they compare using less than, greater than, and equal to. They plot on the number line and compare that value. So 3 compared to 6. So I look at 3 and 6. I know that 3 is back to the left of 6. 3 is less than 6. 5 and 2. I find my 5. I find my 2. I know that I have to go to the right to get to 5. 5 is greater than 2. And you can even see that directionality if we turn these into arrows. Now, throughout elementary school, just like it gets more complex at secondary, it gets more complex there. The numbers are always positive in elementary school, but they get very large in fourth grade, and they get very precise in fifth. So there's a lot of attention to detail. They spend almost their entire elementary school years comparing numbers and labeling value greater than, less than, or equal to. When we get to sixth grade now, instead of just comparing numbers, we're looking for lots of numbers in a set. And these symbols are new. The symbols are new, but the concept is not. And starting in third grade, when they look at data, they'll discuss, how many are fewer than 4. So there's my boundary at 4. I want everything else versus 4 or more. So here's my 4, but I want those now and the ones after it. This would be a great way to launch into these symbols because the concept and the discussions have been had. They just haven't used this notation to talk about it before. So on our number line, that evolution goes from plotting a point at 2 when x equals 2 to now we can be greater than or equal to 2. So I can still equal 2. Everything now that's greater than 2, or everything that is to the right of 2, well, 3 is greater, 4 is greater, 3.5, 2 3/4, 2.25. All of these values are greater than 2. Instead of trying to plot them all, which would be impossible, we just shade to show that everything over there is a possible answer. When we lose the equal sign, I still put a barrier at 2. I need to know where that is. I'm still interested in everything after it, but I'm not going to fill it in because I cannot touch it. I imagine a ball rolling along. It will just fall straight through. There is nothing there. It doesn't equal it. It doesn't touch it. This is just a boundary. And that hole in a graph is really important later on. In 7th grade, now our coefficients can be integers, which means we've got a potential to divide by a negative number. We know that we need to flip the inequality, but let's talk about why. If we stop right here and just talk about what that says, the opposite of x is greater than 4. So when I look at my number line, there's 4, and the opposite of 4 is negative 4. Greater than 4 would be 5. The opposite of 5 is negative 5. 6 and negative 6. So where this is all of everything that's greater than 4, all of these values, if I take the opposite of them, I will get something that is greater than positive 4. That's a lot to go through every single time, which is how we ended up with flipping the inequality. Because we're talking about opposites, when I do this all the way around, I'm going to flip my inequality so that it takes us straight to where all those opposites are that we need. The flipping is the shortcut that accounts for understanding that where one set of values are, the opposites are in the other place. Because of this shortcut, we've got to be really careful now when we end up with variables on both sides. These statements say the same thing. I'm at 4, x is greater or to the right of 4. Four is to the left of all my x's. These are all my x's. Out here on the left is where 4 is. Focusing on this meaning instead of the mechanics will save some headache down the road. When we're solving equations, if we only teach kids move variables to the right, we're creating negatives where they didn't used to be, and we're creating the need to flip that negative. So there's 4 new places that we could make a mistake that don't exist if we just leave things where they are. It's worth the time to focus on the meaning, to me, to be able to keep that safer path. Also, in 8th grade now, we have access to tools to help us generate multiple representations. If we look at our word problem, there's our statement about store S, which shows up here and here, and this is S and S and S. Store T, 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 T. And we want to know when S is less than T. S, T, less than. So we know multiple choice, but when you're ready to start solving, on my graph, it's easy to see. S is literally underneath T. That happens here and everything after that. If I look at my values, these are less. Here they're equal, and now the less numbers are here. So I know that S is less than T moving from 2. We've got these multiple representations to use to help make sense and to help check what's going on. Algebra 1, we're still solving. We still have access to all the tools we can use to verify. We will still put a number on a number line to graph it. We can also continue using the same methods to check that we did when we were using equations, because I can pick a number over here, say 5, and when I evaluate at 5, this is a true statement, so I know I have shaded in the right direction. Algebra 1 is also where we move from single variable to 2 variable inequalities, so we're translating our open and closed circles on a number line to solid or dashed lines in the grid. Y is greater than, so I would use an open circle. Instead of having to make all these little open circles, we will just use a dashed line. They're synonyms. And if I'm standing on the y-intercept, y is greater. The y values increase going up. So I'm interested in all of these points, right, that are above my line. Again, instead of trying to plot them all, which would be impossible, we shade. I can check. Pick 0, 0 when we can. 0, is that greater than 2/3 of 0 minus 3? You bet. This is correct. We know we shaded the right area. We will also do this with systems. And here we want to know where they overlap, right? Where both are true. So if I start, it's greater than, so the line is dashed. And y is greater, so if I'm standing on my line, we're moving up. Greater than or equal to, so the line is solid. Still greater than, so we're standing on the line and going up. And then what has happened is I have this area that they're both pointing at. Again, we're going to grab an ordered pair. I like double ones because then you don't have to worry about where you put which number. And we're going to check, is 5 greater than 2/3 of 5 minus 3? Yes. Is 5 greater than or equal to -5 plus 7? Yes. They both work. We have shaded in the right direction. So when we get to Algebra 2, we're still doing systems, but we're into the realm of what's called linear programming, where now we have several constraints. And we're looking for the polygon that they make when they enclose that area, because it's the vertices that we're looking for that we're going to test to see which of those will yield the results we want. And so when we evaluate here, we didn't try 0, 0 because the question's asking to maximize profit. We find that there's our ordered pair that in context is telling us how many of toy A and toy B this particular problem to maximize his profits. Beyond graphing systems, now we're also going to take solving quadratics and absolute value, and we're going to make them inequalities and solve them. Just like solving equations, we're going to, because it's a quadratic, we want to orient this around 0. And then we're going to pretend that it's an equation. When we solve, we get 1 and 4. 1 and 4. We know that that equals 0 at that point. If I'm looking at my graph, here at 4 and at 1 is where these intersect. Now, to figure out our inequality or our shading on our number line, we're going to use a skill that comes up later on when we're graphing more complex polynomial functions. We're going to pick a point in between and outside, and we're going to evaluate that point back into our function. So if I evaluate at 0, I get 4, which is positive. If I evaluate at 2, I get 4 minus 10 is -6, -2, which is negative. And if I evaluate 5, I get 5 squared minus 25. I get 4, which is positive. And I'm looking for greater than 0. So everything this way and everything this way, which in our graph from here, it is above, and from here, it is above. We're gonna bring in some compound inequalities. Negative infinity to 1, and 4 to infinity. Again, looking at my table, here's 2. Everything that way is greater than 2. Here's 2. Everything that way is greater than 2. Multiple representations to check and help make sense. Just a few examples. I wanted to hit the highlights. So starting in 6th grade, right, we can see we're writing our own inequalities every year. And then on into beyond. We're solving pretty much every year. 8th grade, that's when we first get those variables on both sides. So it's not a tested standard, but does that mean we shouldn't solve? No. Reasonableness comes in all the way through. I hope you found it helpful. Definitely reach out. Let me know if you have any questions or ideas or how we can make things better.